Good afternoon and greetings from Krakow in Poland. First, I would like to thank the organizers of this series of seminars for an invitation for me to give a talk, and thank you very much. Today, I would like to discuss scalar fields in an approach to quantum gravity called Causal Dynamical Triangulations. And I will start with a short introduction to this approach. The second thing will be how to introduce coordinates using classical scalar fields. And the last part will be about dynamical scalar fields and what is their back reaction on quantum geometry. Let me start with answering the question, what is causal dynamical triangulations? And for those of you who are not familiar with this approach, it is a background independent and diffeomorphism-invariant, so a non-perturbative approach to quantum gravity. And it provides a lattice regularization of the formal gravitational path integral. And instead of integrating over geometries, we will sum over causal triangulations. And it's based on well-grounded ideas of quantum field theory, namely path integral formalism, lattice regularization, and Monte Carlo simulations. And we will use Monte Carlo simulations to compute expectation values of some observables defined on those discrete triangulations, which aim to approximate continuous geometries. And this is the formal gravitational path integral. We will regularize the geometry with triangulation. So we are now summing over triangulations. And we also perform peak rotation, which is well defined because of the causality condition, which enforces that our geometries are globally hyperbolic, and we can foliate the triangulation at a geometry with leaves, and we have a distinction between time-like and space-like links, and this allows us to perform the peak rotation. So we end up with a statistical model. We have a well-defined partition function, which now sums over, is a sum over a discrete, infinite but discrete set of triangulations, and we can use Monte Carlo techniques to sum over a sample over a subset of this ensemble and approximate some expectation values. And another difference is that in the continuous we have the Einstein-Hilbert action, but we can also compute it directly on a triangulation, and then we end up with the Regge action, which has a very simple form, and it is just a linear combination of some global parameters like the number of vertices, number of simplices, and number of simplices of some specific type, and with coefficients which are per coupling constant, which depends on the coupling constant in the continuous action, Newton's gravitational constant and the cosmological constant, but also because of the foliation, we have a distinction between time-like and space-like links, and there is also a ratio which doesn't have to be 1 between the lengths of those links. And this introduces another coupling constant, which, even though it seems artificial, it does have an important impact on phase diagram. So our fundamental building blocks are 4-dimensional equivalents of triangles, which we call 4 simplices, and we glue them together so that we form a triangulation with a given topology and would preserve some conditions. And of course, the more simplices we take and the smaller they are, then we can better approximate a smooth geometry. But even though we take 4-dimensional building blocks, so now I'm talking about 4-dimensional Causal Dynamical Triangulations, and the whole talk will be about this model in 4 dimensions. But even though the building blocks are a subset of a four-dimensional Minkowski space, it doesn't mean that if we glue them randomly in some way, it doesn't mean that the triangulation is also four-dimensional. So Lego blocks is a good example where you can take a three-dimensional block, and if you just stack one on top of another, like here, you get something that is effectively one-dimensional. You can also create something two-dimensional and also a three-dimensional block. But if you glue it randomly, you can get something that has a fractal dimensionality. So the dimensionality of the building block doesn't determine the dimensionality of the whole triangulation, and it might depend on the scale. And this is something that we observed, that we have a scale-dependent spectral dimension, for example. Again, because of this foliation, we have layers of, we could say, of constant time. And in CDT, this is also discretized. So we can talk about a layer at time t. We call it a slice, and also at t+1. And as four simplex always joins or connects two adjacent layers, so t and t+1, and so on. And this means that you can have two types of simplices, or in fact, four types, depending on the number of vertices in each layers. A four simplex has 5 vertices, and it can has four vertices at slice t, let's say, and 1 at t+1, and this is a 4-1 simplex. You can also have a mirror reflection, so you have 1 at given slice and 4 at the next slice. So this would be 1, 4. But you also can have a situation where you have 3 vertices at slice t and 2 at t+1. So this is a 3-2 simplex. And because they can have a different geometry, because the length of the time-like and space-like edges are different, this introduces another coupling constant. And now, so let's state the setup is that we have a triangulation that is built of 4-dimensional simplices that are glued together. And we also choose the topology in such a way that the leaves of the equation have a toroidal topology, and we also have a periodic boundary condition in time. So the topology is like T3 cross S1, which would be T3 cross T1, which is just T4. And now we can put scalar fields on triangulation. And the first approach is to put non-dynamical scalar fields. So we just are given by Monte Carlo simulations a triangulation, and we put scalar fields on top of it, and there is no back reaction of the field on the triangulation. There is no coupling in the action between the scalar field and the triangulation. And we don't want just to put a classical scalar field. We also want some properties for the scalar field. Because otherwise, if we would like to have a scalar field that minimizes free scalar field action, it would be just constant everywhere. But we modify this slightly by stretching the scalar field. And let me describe how we do it. And we want those scalar fields because then we can use those scalar fields as coordinates on this triangulation. And I will also talk about that. Now, we assume that the scalar fields will take values in a circle. So the target space is S1, and we have 4 scalar fields, and they are required to wind once around S1 when we go in one of the 4 directions. Because the topology is T4, we can basically define X, Y, Z, and T directions, and then require that when going along this direction, for example, here, the scalar field that is defined on this triangulation or this geometry is required to wind once. And for a toroidal topology, the global topology of our spacetime is T4, T3 times T1, where T3 is the topology of spatial leaves or slices, and T1 is the topology in the time direction. We can define 4 non-contractible and non-equivalent three-dimensional hypersurfaces, which we'll call them boundaries. So here you have a two-dimensional example of a torus T2, and we can define 2 non-contractible and non-equivalent one-dimensional hypersurfaces, which are denoted with this red ring and this blue ring. So it's not possible to continuously contract them to a point, and also to transform one into another. And we need those boundaries to introduce a jump of the scalar field when it crosses this boundary. And the boundary itself is non-physical, so its exact location is not important. It is only used to stretch the scalar fields. And in the two-dimensional example, we would have 2 scalar fields, phi x and phi t, for example. For each point, you will have some field values, and you will use these field values as coordinates. In CDT, the geometry is just built of triangles or 4 simplices, and the scalar fields live inside in the center of each 4 simplex. So you can assign these 4 numbers, 4 values of the scalar fields to each simplex and use them as coordinates, and they will change more or less continuously from 0 on one side to 1 on the other side, and some values in between, and then they will grow as you go around in a given direction. Of course, our triangulations are nothing like the smooth torus. They're much more fractal, but you can also, the topology is what's important, and you can also define those boundaries and define corresponding scalar fields. Just remember that the scalar fields are classical. You first are given a triangulation, and then you find a classical scalar field on this triangulation. So how we do it, we just take classical scalar fields, which minimizes the action for a real massless scalar field. And here we assume that it takes value on inside a circle S1, and this is achieved by adding a jump matrix term to the action, which enforces that it winds once in a given direction. So if you discretize the continuous action, you just get a sum between all neighboring simplices, and you take the square of the differences between the field values. So this is just a discretization of the square of the derivative of the scalar field. And we assume that this scalar field has periodic boundary conditions, and there is a jump at the boundary. And the jump is introduced by this Bij term, which is 0 almost everywhere, except at the boundary. If going from simplex I to J crosses the boundary in the positive direction, it is +1. If it crosses in the negative direction, it's -1. So it's an antisymmetric matrix. And this means that the simplex on, let's say, J on one side of the boundary observes a shifted value of its neighbor on the other side of the boundary by this Bij term. And this is equivalent to taking that phi x has values in S1, and requiring that it winds once in given direction. Again, there is no impact of the scalar field on the quantum geometry. And so we start with this classical, with this discrete action, and we want to find a classical solution which minimizes this action. And it's given in terms of the Laplacian matrix for our triangulation. And it's minimized by a solution to the Poisson equation, where L is the Laplacian matrix for our triangulation. So it captures the connectivity between simplices, and B is the jump vector, which is just a sum of rows in or columns, doesn't matter, of sum in a row of the elements of the jump matrix. And so now all we have to do is to solve this equation. There are some technical problems, and also this L matrix is rather large. It's like 1 million times 1 million simplices, but it's a sparse matrix, so we can do it. And also changing the boundary, the position of the boundary, like it's, for example, here the boundary is here, changes the solution, but in a trivial way. So the solution transforms trivially under boundary redefinition. And this is what we want to have, because the boundary itself is non-physical. So the exact location is not important. You can always shift your scalar field by a constant. It will be still a classical solution, and taking into account the periodicity, because it's on S1. So the effect of this jump is that it stretches the scalar field in some interval. It's not necessarily from 0 to 1, even when the jump size is 1, but you can always choose the boundary so that it will be stretched in this interval. So it's the easiest way to see it in one dimension. If you introduce a jump between the black bead and the white bead, and you want to minimize this action, you just stretch it so that the change is always is more or less constant. It continuously changes from 0 to 1. And indeed, if the black bead observes the value of the white bead, which is 0, shifted by 1, it would be like here. So you can see that this jump just introduces a stretch of the scalar field. So indeed, if you do it in a two-dimensional case, it behaves more or less that it's 0. The value of the scalar field is 0 on one side of this boundary, and it continuously grows when you go around in a direction orthogonal to the boundary. It goes through 1/2 up to 1, and then there is this jump. You can also have some bubbles, and then it's possible that the value is, for example, from 0 to 1.5, but you can always redefine your boundary so that it's always between 0 and 1, and that's because it's on S1. So, for example, and the circumference is 1, so value 1.5 is the same as 0.5. Okay, and in the two-dimensional case, you could also have an orthogonal boundary, and then if you were to go in this direction, the second scalar field will also continuously grow from 0 to 1. And they are a solution. The classical scalar fields are a solution to the Laplace equation, or technically to the Poisson equation, but from a physical point of view, it's more like a Laplace equation, because this B term is not really physical. It's if you take it on a S1, it's just like requiring that it winds once in given direction. So the classical solution is just minimizes this action, which is the discretization of a free massless scalar field action. Okay, and now let me show you some nice pictures. And let me first describe what is what. So we start with a single triangulation. A single triangulation is not really physical. It's like a single path in a path integral, but it still can give some meaningful information. And this is what we'll do here. We just look at a snapshot of some path in our path integral, which is a triangulation. It has a T4 topology. We introduce these 4 boundaries, which are non-contractible and non-equivalent. In fact, we keep the boundaries the whole time during the Monte Carlo simulations, because it's not easy to introduce those boundaries once just given a triangulation, but this is a technical detail. So we have these 4 boundaries, and we also have 4 basically independent scalar fields. And each scalar field, it has a jump at a respective boundary, or it just takes value on this one and winds once when going in given direction orthogonal to given boundary. And we have 4 boundaries orthogonal to directions x, y, z, and t. And therefore we have also 4 scalar fields, phi x, phi y, phi z, and phi t. And then for each simplex, there is the set of 4 fields living inside this simplex. And so we have 4 numbers for each simplex. And those numbers will serve as coordinates on this plot. And unfortunately, it's not easy to plot something in a 4-dimensional space on this flat screen here. So we project it just on these 2 directions, 2 coordinates. So this is a projection on the phi t and phi x. Phi y and phi z, you can imagine they are orthogonal to the screen. And each simplex, each pixel, each color pixel on this plot denotes a single simplex. So 1 pixel is more or less 1 simplex, unless they just project on the same pixel, which is visible as brighter and darker areas. And the color is also connected to the original time coordinate of the foliation. So phi t is computed somehow with a boundary which is given by one of the slices, but it doesn't mean that it agrees exactly with the original time coordinate. But it does more or less, which you can see that the color changes gradually from yellow through green, blue, red, and then to yellow again, because it is periodic. And you can see that there are some dense regions and fibers, and those dense regions correspond to outgrowths. And because they have some, it seems like they have some time extension or even spatial extension, it means that the outgrowths, they propagate in time. So there's an outgrowth that moves in time, and so they are preserved for some time. And this is in the de Sitter phase of CDT, which is one of the nicer phases, because it does have the most classical properties. It behaves like a well-defined 4-dimensional object, and the Causal dimension is around 4, and the spectral dimension varies from 2 to 4. There are no infinities, no zeros. So it seems like this would be the world in which we live. Okay, we can also look from another angle on the same picture, and now we look at the projection phi x on phi x, phi y, and we see that the outgrowths, they also have a spatial extension, and the time direction is also orthogonal to this screen. So we see some very nice picture of cosmic voids and filaments, where dense regions would correspond to large volumes, which can be surrounded, large volumes, but surrounded by a small boundary. Okay, and now let me justify why dense these fibers or dense regions, why do they correspond to outgrowths of our triangulation, of our geometry? So each, just to repeat, to sum up what I told before, each simplex is assigned coordinates phi x to phi t, and because there is solution to this Poisson equation or this Laplace equation, the value at given simplex is just equal to the mean of the values of the scalar fields of its 5 neighbors. Every simplex has 5 neighbors because it has 5 sides. Those neighbors also have some coordinates, and the value inside the simplex is just the mean of its neighbors up to the periodicity, up to the jump at the boundary, which is non-physical really. And this means that those coordinates, they preserve the structure of a triangulation, because a value of the coordinates of given simplex is just the arithmetic mean of its neighbors, which is what you would more or less expect. And if something lies in the middle of some other things, then its coordinates should be also in between. And in such case, we observe this remarkable pattern of voids and filaments. Because now let me look at this two-dimensional visualization of some geometry with some outgrowths. Now you can cut this triangulation, this geometry along this two, in this case, boundaries. So you will get basically a square with some outgrowths, and now you can flatten this geometry. So from a triangulation point of view of a triangulation, you will have a lot of small triangulations, and now this scalar field changes from, let's say, 0 to 1 here, but because a dense region of small triangles, which corresponded to an outgrow, like for example that one, if you cut it first along the boundary, you will get this one, and then if you flatten it, you will get something like that. You have a large number of triangles with a small boundary, and this means that the scalar field changes here by a small number, and even here by a smaller, the change when you go from one triangle to another is even smaller. So this means that the coordinates change very slowly inside an outgrow, and this is visible by this dense cloud of points, because they are close together in those coordinates. Okay, let us see how those pictures, this density maps, look for.
Sorry, Andrzej, can I ask a question on this? So this is the classical scalar field, so quenched and no back reaction on the geometry.
Not yet.
So it really is a probe on your geometry. So it kind of, the scalar field kind of like tells you that these outgrowths, that these outgrowths are there. Yes. But why? So wouldn't I have expected that I would see something like this also on the level of like the volume profile if I compared it? Because at least
I also
like at least like these branch polymer or baby
and,
universes.
I will also show, this will be maybe, you can also take a surface of constant value of given scalar field and measure the volume here, and this is presented here on this axis. So you can measure how many simplices are basically crossed by a surface of constant phi t, for example, and then compare it with the original t. So this would be this, and t here is the volume profile measured in the original time coordinate, and n of phi t is measured using this phi t. And I will also talk about this this later.
And so, what is the, like, if you take a typical triangulation or like a typical lattice configuration, what is the overall volume that is in the outgrowths and not on the smooth?
It's a tricky question because it really depends how you define an outgrow. And
right.
For example, is this an outgrow, or maybe the whole rest is an outgrow? So it's it seems like a large part is it depends on the phase and so on. So, but it seems like a large part is in the in outgrowths depending on your conditions.
But so if I remember back to like standard CDT talks, there was always the point that you have like the de Sitter volume profile. So if you look at the Schelling function that you get by like with cosine cubed.
Yes, this was for spherical topology, spatial topology.
Okay.
And here I'm talking about, but for a sphere, I didn't show it here, but for a sphere, it's hard to have this 4 non-contractible boundaries because they will contract to a point. So that's why we use toroidal spatial topology. Let me go to the next slide because I still have I'm back of time. Okay, so as I said at the beginning, the Regia action is quite simple, just a linear combination with some global parameters and 3 coupling constants. One of the coupling constants, it plays a role of the cosmological constant, and it just it just steers or the it defines the average volume. So we are not free to choose it. It has to be more or less tuned to its critical value. Otherwise, the total volumes or the number of 4 simplices, it either shrinks to 0 or explodes to infinity. But we are free to choose the 2 other coupling constants, K0, which is basically analog of the inverse of the gravitational constant, and the asymmetry factor delta. Delta equals 0 means that there is no asymmetry. And therefore we can show the phase diagram on a plane, and we have so far we have found 4 phases. And let me now show how these density maps look in those different phases. So in phase A, if you look at the volume profile, you have like a series of maxima and minima. So you have a series of independent universes. And you can, if you show the density plot as before, this is the phi t, phi x projection. So you are given a triangulation, which is a typical triangulation in phase A. You add those boundaries, you find classical scalar fields, and you plot it. So you can see that the plot is clearly different. You have some regions, denser regions, which are rather irregular, and they seem like independent. And if you look from the side, it also, you have just some patches of independent denser regions. So it's definitely very different from the plot in the de Sitter phase, which the de Sitter is more meaningful for the spherical topology, but we still keep the name for the toroidal topology, even though the volume profile was not cosine cubed but just more or less constant. In the bifurcation phase, you have vertices of very high orders, which means that there are vertices with many simplices around. And even though the volume profile or the properties of the bifurcation phase look quite similar to the de Sitter phase, the picture using those density maps is completely different. There are these kernels with a large number of points, of pixels or simplices around it. And so this means that the field value around this, that the field is localized around this this kernels. And if we look from the side, it also looks quite localized. And we also have a phase B, which is completely a collapsed phase where the whole volume sits in one slice, and it's even more localized even in the field coordinates. So this was only to show that the picture using those density maps looks completely different for different phases. So it is like a good tool to maybe measure, to decide if given configuration belongs to this or that phase. And it's nice that it gives the pictures are very different for different phases. And now let me jump to the interesting part, where there is a back reaction of the scalar field on the quantum geometry. And we can ask the question, what is the effect of those dynamic scalar fields on the underlying quantum geometric degrees of freedom? So we take the same action. We require that the target space is an S1, that the circumference of the target space is delta, and that each scalar field winds exactly once in the respective direction. And previously, the circumference was not important because the classical solution is scaled just with delta. But now, delta is important. If you take large delta, you're stretching the field more, and the classical solution will be more important. So if you take the discretized version of this action, it decomposes into the quantum part, which does not depend on delta at all. It only depends on the Laplacian, and eta is just the deviation of the scalar field from the classical solution. And the second part is the classical part, which depends on the triangulation. That is number one. Here, L also depends on the triangulation, but it scales as the classical part scales as delta squared, which means that for small delta, the classical part would be not important, and this thing will dominate. But for large delta, the classical part may become important and can dominate the action, and it will, indeed, this is what will happen. Now, the quantum fluctuations can be integrated out, and they will just give the determinant of the log of the determinant of the Laplacian up to getting rid of the zero mode because of the invariance under translations of the scalar field. But it seems that the impact of those quantum fluctuations of the field is negligible. So no matter what is the delta, it only slightly shifted maybe the positions of the phase transitions, but basically we didn't observe much impact of those quantum fields. So for delta equals 0. But this requirement that the scalar fields have to wind once around the target space of circumference delta means that for large delta, the classical action, which is just the action calculated for the classical solution, becomes important. So indeed, for small delta, the geometric part of the action, which was not shown here at all, it's just a standard reg action, will dominate. But for large delta, the matter action may dominate in the total action, and triangulations or geometries for which this classical action is smallest can dominate the path integral. And as we'll see, pinched configurations are those which are preferred by this action, and that they will appear more often, or they will dominate the path integral for given for large values of delta. And now let's consider just a single scalar field that takes value on S1, and it is required to wind once in S1 when we go along the time direction, and it has to jump basically from it has to go from 0 to delta and then jumps back basically to technically back to 0. So on this axis we have the time direction, and t is the original time coordinate. It enumerates foliation, and nt is the number of simplices or tetrahedra in given slice. And for small values of delta, so for small circumferences of the target space of the scalar field, the volume profile is more or less constant, as it is without the scalar field at all. But once we cross the threshold and go to larger deltas, we observe a cosine volume profile, not cosine cubed, but cosine. But there is a clear jump. So it seems like a first order transition from a constant solution to a cosine solution. And can we explain this? Yes, we can, using a very simple mini superspace model, where we assume spatial homogeneity and isotropy, both of the geometry and the scalar field. So we assume that the metric depends only on t, on time, and the scalar field also depends only on t. And under such assumptions, the Einstein action with including the matter term, it can be simplified to this form, and under some constraints that the global volume is constant and that the field stretches from 0 to delta, we have two solutions that minimize this action. One is a constant solution, and the second is a cosine solution. And indeed, so a constant solution and a cosine solution, and they compete with each other. And when you compute the value of the action for those solutions, the constant solution has a smaller action for small delta, below 2 pi over square root of g, and the cosine solution has a smaller action for delta above this threshold. And this explains why we have this jump from a constant solution, which is the same as without any fields, for small delta, to a cosine solution for large enough delta. So depending on the circumference of the target space, we get different behaviors. So this was just a single scalar field. And now, so this was the density. Here I described the density maps as they were before, but so to generate the plots that I will just show, we forget about the dynamical scalar fields. So as an input, we have a triangulation with dynamical scalar fields. We throw away the scalar fields and put again classical scalar fields only to make the pictures. But to summarize the previous part with a single scalar field winding the time direction, we indeed observe that for small delta, the geometric part of the action dominates, and there is really no change between no field at all and small delta. But for large delta, the matter part of the action dominates, and triangulations which minimize the classical action for the scalar fields will appear more often, and those triangulations are the ones that are pinched. So by pinched, I mean that they go to almost 0 here, so this cosine solution, because in this region the field can change quickly, rapidly, with a small impact because the volume is small. Okay, so now what happens when we add 3 dynamical scalar fields that wind in the spatial directions, x, y, and z. And we can put those fields on a triangulation and use them as coordinates to visualize a triangulation. And this is just a projection on phi t and phi x. So those are not really, the triangulations itself were generated using dynamical scalar fields, but the plots here, the pictures, were generated using classical scalar fields, and we can project them on phi t and phi x. So this is when there's basically no scalar field. This is the sitter phase without scalar fields. This is with 3 scalar fields, and for each of them, the circumference is 1. So the jump parameter, the delta, is 1. And let's see what happens when we increase the circumference of the target space. We see a formation of some fibers. So the field value is localized. So this is phi t on this axis. And this is phi x. And again, the scalar fields wind in the spatial direction. So they wind in this direction. And this explains, as before, so here we had this cosine. If we had a single solution in the time direction, we observe a cosine solution for the volume profile. And similar happens here. Because phi x is required to wind once. Once we cross this threshold and delta is large enough, phi x becomes localized around some value. And the same is true for phi y and phi z. So we more or less understand why this happens. And we increase further delta, but then something strange happens. The scalar fields become localized also in the time direction, even though there is no scalar field that winds, no dynamical scalar fields that winds in the time direction. And moreover, we start to observe, and then it basically collapsed to one point. But if you look at the volume profile for those large but not too large values of delta, for example, delta was 7, this is cosine cube, exactly like for a sphere. And if I will have time, I will try to explain why this happens. And now let us look at exactly the same pictures, but from the other side. So now it's a projection on phi x and phi y. No scalar field, delta is equal to 1, and it increases. We observe localization in space, and then it only this localization increases. Okay, and so let's look more closely when delta is equal 7. If you look at the volume profile, it is again very well described by the cosine cube formula. So here is the volume profile. T is the original time foliation, and what's plotted is the nt number of tetrahedron given slice, or the average value. And on this plot, we have these pixels using the coordinates given by scalar fields. And now we can again explain why we have this cosine cube, why from a constant volume profile, it's jumped to cosine cube. It is because a large enough jump in the time direction introduces a pinching of the triangulation in those spatial directions. So to repeat, a large enough jump or circumference of the target space of a scalar field winding in a spatial direction introduces a pinching in the spatial direction, which means that we effectively change the spatial topology from a toroidal one to a spherical one. And we know that, so we pinch it here, we end up with something that effectively looks like a sphere. So the spatial topology changes from a toroidal one, effectively from a toroidal one to a spherical one. technically it's always have to be a toroidal one, but just this thing here can be very small, and then it's irrelevant when measuring some expectation values. So this means that the central part with the hole or the genus, it just shifts to a very small outgrowth, which just becomes irrelevant when measuring global properties. And we already know what is the expected volume profile when the spatial topology is spherical and when it's toroidal. And we know that for toroidal spatial topology, the volume profile in the de Sitter phase, in the C phase, is constant. And we can explain it by measuring the effective action, while for a spherical spatial topology, we have an additional term in the effective action, and the solution is now cosine cubed. And this is exactly what we observe. So the change is twofold. First, scalar fields winding in the spatial direction introduce a pinching in spatial direction. This changes the effective, this introduces the effective change of the spatial topology from a toroidal to spherical. And this, in the next step, changes the volume profile in the time direction from a constant one to a cosine cube, to a blob-like. And it can be explained by this effective action. And the difference that we observe is indeed what we observe from for previous simulations without scalar fields for spherical and toroidal spatial topology. Okay, and I will conclude here. Okay, it's not the latest slides. Anyway, so just to sum up, CDT is a model of generic geometric fluctuation at the Planck scale, and we can introduce coordinates on spacetimes with toroidal topology using classical scalar fields spanning in some interval. And we can use those coordinates as some observables that gives us information about phase transitions of the phases itself. And fractal outgrowths are visible as dense clouds of points, and you can see that they indeed propagate in a more or less coherent way in time. And using those coordinates, we observe this remarkable pattern of voids and filaments, which qualitatively looks quite similar to the pictures of voids of filaments observed in our real universe. And introducing dynamical scalar fields with matching topological boundary conditions has a dramatic effect on the geometry. For large enough coupling, or this delta parameter, we observe a transition or phase transition for the geometries. So we change the change of the topology, which most likely would trigger a first order phase transition, depending on the value of this delta parameter. And also the mini superspace model is able to explain this phenomenon in a quite good manner. And I will thank you here.
Right. Thank you very much, Andrzej, for the nice talk. Let's thank Andrzej. All right.